Hi everyone, welcome back. This is our last video segment. We just saw this very interesting number e. There's another number that's pretty interesting. It's the number I. It's got a bad name. I won't say what I stands for. But it's defined such that I squared equals negative 1. For example, if we take this equation x squared plus 4 equals 0, the two solutions of that are x equals 2i, because if I take 2i and I square that, I get 4i squared, in other words, 4 times negative 1, so I get negative 4 plus 4, which is 0. And the other one is x equals negative 2i, because when I square that as well, I get a negative 4, and negative 4 plus 4 is 0. Now I know many of you don't believe that these are solutions to this, and that's fine. But what I will point out is that if you had seen the equation, not you personally, but some of your relatives, a long time ago, not that long ago, had seen this equation, 2x plus 4 equals 0. They would have said that equation has no solution, even though you just instantly say, oh, that's x equals negative 2. Because back then, people didn't believe that you should have negative answers as solutions to equations. So my claim is that several generations from now, our or your great-great-great-great-grandkids, who knows, will look at an equation like this and think these solutions seem just as natural as to you a solution of this, x equals negative 2, just as that seems pretty natural to you. So let's consider going with this number I. Well, we just saw this great number e. Let's put them together. Let's make up a new function, e to the ix. I'd like to figure out how we could evaluate this. Like if I plug in the number 3, what would it mean to say e to the I times 3? How can we find the value of this function? Well, let me make up a new function. I'm going to make up a function f of x. I'm going to call it cosine of x plus I sine of x all over e to the ix. Why am I making this up? You have no idea. That's fine. But here it is. It's a function. It's got this e to the ix in it. It's also got our two favorite trig functions, and it's got an I in there thrown in as well. Well, this is a calculus class. When somebody gives you a function, what do you do to it? You take its derivative. So let's find f prime. So I'm going to take the derivative of this. What rule are we going to need to use for this? Of course, the quotient rule. Quotient rule says we start by taking the derivative of the top. So the derivative of cosine gives me negative sine. I is a constant, right? So we just treat it as a normal constant using our constant multiple rule. So it stays there when I take the derivative. And the derivative of I sine of x is I cosine of x. And we're supposed to multiply that by the denominator, e to the ix. Then we subtract. Now we leave the numerator alone, cos x plus I sine x. And we take the derivative of the denominator. So I've got e to the something. So what rule do we need to take the derivative of e to the something? We need the chain rule, right? So the derivative of e to the something is e to that very same something, but then times the derivative of the something. But this I is a constant, right? If this had been e to the 3x, the derivative would be e to the 3x times 3. So this is e to the ix times I, all over the denominator squared. So let's see what happens here. On the top, I can see that I've got an e to the ix in both of these terms. So I can factor out an e to the ix. And let's see what's left over. There's a negative sine x here. There's an I cosine of x here. From over here, I've got this negative times the cosine of x times this I at the very end. So that's going to give me a minus I cosine of x. And I've also got this negative times I sine of x times an I. So I've got a negative I squared sine of x all over e to the ix quantity squared. Well, I hope you're noticing some nice things are going to happen here. I've got this I cosine x and a minus I cosine of x, so those cancel. I've got this negative sine of x, and here I've got negative I squared. But what is negative I squared? I squared is negative 1, so negative I squared is 1. Meaning this is really the same as saying plus sine of x. So these two cancel as well. And what are we left with in the numerator? E to the ix times 0. So this whole thing equals 0. No matter what x is, the derivative of this crazy function that we made up is always 0 for every single x. So what does that tell you about what the graph of this function f of x looks like if its derivative is always 0? What must the graph look like? I hope you're picturing a horizontal line. This means that f of x's slope is always 0. So thus, f of x is a constant function. It always equals the same number. Can we figure out what that constant is? What is that constant? So if we can figure out the value of f of x at one x value, then that's the same as the value of f of x everywhere, because f of x is a perfectly horizontal line, because the slope of f of x is always 0. So what would be a number that I could actually plug in here and get an answer? I can't plug in like 7 because I don't know what e to the I times 7 is. What's the only x value that I'm going to be able to plug in here so that I can evaluate this denominator? It's 0. So f of 0, we're going to get what? Cosine of 0 plus I sine of 0 all over e to the 0. Because I is a constant. If I multiply it by 0, I get 0. Well, what is cosine of 0? That's 1. What is I sine of 0? That's 0. What is e to the 0? That's 1. So this is 1. So that's telling us that f of 0 is 1. That means this function is always equal to 1. Since the slope of it is 0, if its y value is 1 at one point, then the y value stays 1 forever. So what does that tell us? So our function, f of x, which we created as cosine of x plus I sine of x over e to the x, e to the ix, equals 1 for all x. So now you've got a fraction that equals 1. What does that tell you about the top and the bottom of the fraction? They've got to be the same, right? Thus, this thing that we were trying to evaluate, e to the ix, the denominator must be the same as the numerator. So e to the ix must turn out to equal cosine of x plus I sine of x. This e to the ix, this crazy function that we made up out of our number that we really like e, and this new number I, turns out to involve our two favorite trig functions. How would you ever guess that? Well, our old friend Euler guessed it. This is called Euler's formula, one of many things named after Euler. One of the most famous formulas in mathematics, certainly. A way to relate our exponential function and this number I to our two favorite trig functions. How would you ever think in advance that that would happen? All right, one more thing. I'd like you to think now about what you imagine as the 5 most important numbers in the universe. Write them down, pause the recording, write them down, and we'll see if we all agree. Okay, welcome back. Usually, when we're all sitting out here and I ask a bunch of people here to vote for the 5 most important numbers, they do pick the same 5 numbers that I like, that I would pick. So let's see if you have picked the same 5 numbers. Before that, let me just say that I have really enjoyed teaching these videos and creating the applets and the website and all of that with plenty of help from a lot of people whom we're going to thank in the website by name. And I hope that you have enjoyed this as well. This is something that we're starting out. First time we're trying to teach the class this way with these shorter video segments and a lot of interactive applets for you to work on and check your understanding quizzes. And we hope that it's been a good experience for you. So let's choose here the 5 most important numbers. Well, I hope by now that we've convinced you that E is one of them. If we haven't convinced you that E is one of the 5 most important numbers, then we have failed for sure. So let's choose E is one of them, no doubt about it. I bet almost all of you chose pi. In fact, I would bet every one of you chose pi. Well, we just saw this number I. That seemed pretty cool. So I suspect a lot of you chose I. What was the very first number of them all? Almost certainly it was the number 1. And if we hadn't had the number 1, we wouldn't have had any numbers at all. And then the last one is a number that if you study anthropology, when a culture comes up with this idea of this number, it is considered a huge step forward because it makes so many computations more easy. And that is the number 0. So for me, I would vote as these are the 5 most important numbers. You can see if you agree with the ones that you wrote down there as well. Well, last thing to do here. Here's an equation that's got 2 of our numbers in it. It's got the E and the I. So let's put one of our other numbers in for x. Let's put in the pi. So according to the equation that we wrote up here, Euler's lovely formula, e to the I pi should be cosine of pi plus I sine of pi. Now let's figure out what that means. So e to the I pi, cosine of pi, we're way off on the other side of the unit circle, that's -1, plus I sine of pi is 0. So this says that e to the I pi equals -1. That's got an equation that has the 4 of your 5 numbers all in one without any other numbers. But wait, what if we move that 1 to the left side of the equation? We put 4 of your 5 numbers together on the left side of the equation, and guess what do they equal on the right side of the equation? They equal your 5th number. This deserves a double box. This is an equation that people find truly inspiring and truly beautiful. There was an issue of a magazine called Math Horizons, which devoted a 2-page color spread in the center to just photos of tattoos of this that people had gotten tattooed on their bodies. Different mathematicians have looked at this in different ways. So there's a famous mathematician at Harvard called Benjamin Peirce. He taught here in the 19th century for close to 50 years. And when he proved this on the board, he said the following very famous thing. He said, "Gentlemen," now at the time Harvard was all men, so that's why he said gentlemen. He said, "Gentlemen, this result is absolutely paradoxical. We cannot understand it and we don't know what it means, but we have proved it and therefore it must be the truth." And that's definitely one way to look at this equation. Another way to look at it, the way that I would prefer to look at it, as many other mathematicians look at it, is that this encodes into such a small space this great amount of beauty, and therefore I like to think of this just the way that I would think of a wonderful and very elegant and beautiful poem. And we'll leave you to think about that.